for structured support vector machine. And this is work due to many people, but one of the prominent names in the area is Thorsten Joachims, who with his co-author, he's at Cornell, I think, who together with his co-author has written many of the influential papers in the field. So, structSVM. We need a couple of ingredients. We need a training set. So these are pairs of typically structured observations xi and yi. So when we were talking about MRFs, I usually called the observed input, I usually called O, but to be compatible with the notation in the field today, I use X. So this would be a usually structured input, and then Y is the corresponding structured output. So an image labeling or a graph labeling. And these superscript indices are now over not the atomic element, but over a whole example. So let's say xi would be the ith image in my training data set. I also need a feature function or a feature map depending on a structured input and output, which tells us something about the relation between x and y. And importantly, this thing has a fixed dimensionality. This is important because, let's talk about images. It could be that x1, my first image, was of dimension 256 squared, and it could be that x2 was an image which was 384 squared. So the images could be of, my inputs could be of different size, but this feature map always has the same dimensionality, regardless of the size of the input x or the output y. And let me give an example of how this could look like for our running tracking by assignment example. So for tracking by assignment, X would be my set of detections. And it would be, well, it would really be, no, let me say differently. This is my pair of images. And from this pair of images, I can run my detection procedure and then compute all kinds of features. and establish these associations for possible hypotheses, etc. And then I could, for example, say that one element of my feature map is a summation over all the associations in this particular pair of images. And for each association, I would take the distance of the two targets involved and sum over those distances, but only for those associations which are turned on, because my feature map depends not only on the input, but also on a given output, where this would be a set of active or inactive associations. So random variables that I've put to 1 or to 0. And here by multiplying, so here I would sum over only the distances of the associations that have been switched on. And we have much freedom in the design of this feature map, which is at the same time good and bad. It's good, we can inject our domain knowledge, and it's bad because it's not an out-of-the-box method. Now we have to put some brains into this. But it could also be that the square of the Euclidean distance is meaningful in telling me what is a good configuration of associations and what is a bad one. And it could also be that the third power is meaningful, etc. We don't know in advance. And the aim of this learning is to let the computer figure out how to weigh these different contributions in distinguishing a good tracking from a bad one. So far we've looked only at the distances between detections. We certainly want to look at, for example, the size differences of the associated targets. So the size difference of the ith association, I could take the absolute value of this and only sum up the size differences of the active associations. Or we could do things like take the absolute value of the difference between the total intensity or if you can think of some shape measure. All of these are things that you can put into your feature map. And given enough training data, then the more the better, because the computer, of course, does not see the raw data. So let me again show the example I had. So let's assume that we want to track these cells here. The computer does not see the image that we see. The computer only knows the features that you pass on. So if I'm comparing here two frames, if all that you pass on are the positions of the detections, then in this particular example, which is relatively simple, this might even be enough. But let's say if you sample less frequently in time and things can move further, then using, or if you have a denser picture, more detections, then using just the positions will no longer be enough. Then you will want to use things like, or as a human, you do not only look at position, you also ask, are these things actually similar or not? Does it look like a good match? And all these cues that humans use in establishing an association, all cues that are useful, you would like to pass on to the computer. And you do that by means of this feature map. We then also need, as further ingredient, so I'm still listing the ingredients here. As a further ingredient, we need a score function. That for the structSVM needs to be linear in the parameters which you want to learn. So the score is often called F or S. Again, it depends on the structured input and on the structured output, and implicitly on the parameters which we want to learn. So we will associate one entry in the parameter vector with each of these elements in the feature map. We also need the set of feasible outputs. I'm writing script Y that are associated with some structured input X. So for our tracking example, the permissible outputs would be all those where each cell has a single fade and a unique past only. And for the most frequently used variant of the structSVM, we also need a loss function. That gives the penalty associated with predicting Y rather than our ground truth from the training set YI for input XI. So those are the ingredients that we need to formulate our learning of the parameters W. The structured learning of the parameters W. So I could say I want to find the parameters W such that the score of the true solution so writing the inner product here with somewhat different notation. This is the score of the true output associated with structured input Xi minus the score of some other output Y I could require that this score be not just the differences in the scores. You know, I could also require that this difference be non-negative. And this is actually what's done in the structured perceptron. But in the support vector machine, one prefers to have a bit of a safety margin. and this margin is here set to 1. And this should be true for all I in the training set. And it should be true for all permissible outputs that are associated with the input xi, except, of course, the true solution. Because if I insert the true solution, then I will get out the score of true output minus score of true output, which would be 0. The difference would be 0. Okay? Now, fundamentally, this equation can only be solved if these two sets are linearly separable. So if I plot the score here, and let's say the score of the true solution is here, and the score of the wrong solutions is here and there and there, and you know there are typically exponentially many wrong solutions. And let's say that our desired margin should be of length 1. Then if the data is separable as I've shown here, then I could always satisfy this equation here by simply making W very large. So if the inequality holds with a larger than greater than or equal to 0, then it can also be made to hold with greater than or equal to 1 by just inflating the length of W. However, if I really want a margin of 1 or more, I should normalize the length of W, or I can also say I want to introduce a prior regularization term that makes sure that W does not become too long a vector. And here, typically an L2 regularization is used, even though one could use an L1 regularization also. So this is a regularization term. So at this point, what do we have? We have a function with an optimization problem where the objective function is quadratic in W, and this is why typically this particular form of regularizer is used, because it's mathematically so tractable. And we have constraints that are linear in W. And by the way, the one element of this feature map, so however many entries you have, you should always have an element of 1 in there to allow creating a bias. Okay. So we have an objective function that's quadratic in W in the parameters and constraints that are linear in the parameters. This is a standard so-called quadratic programming problem. For which there are efficient solvers around. It's a convex problem, so we are guaranteed to find the global optimum. So this is very well. But we have one practical problem. Can you think what this could be? Yes. Yeah, you're totally right. So Y is not so large a set. We have n training examples, and typically n is not so huge because somebody needs to generate this training data. So let's say perhaps for the tracking problem, perhaps a friendly person has annotated 100 pairs of frames. 100 is not much. However, for each pair of frames, I have one correct association or one correct tracking, and then zillions of wrong trackings. And these zillions, so a number that's typically exponential in the size of the input, this is the problem. So these are too many to even write down explicitly. So I could, in principle, evoke such a standard QP solver. In practice, there are too many inequalities. So we need to somehow find an approximate or a simpler expression. And one typical approach is to use a procedure called cutting planes, and an alternative is to do stochastic gradient descent. So you're right, we have a problem, namely we have exponentially many constraints. And popular alternatives are to resort to cutting planes procedure or stochastic gradient descent. So this is the cutting planes algorithm for learning a structSVM is the main thing I still want to talk about today. I'll then show you results on application, perhaps talk about latent structSVM. So the cutting planes algorithm for structSVM. Another word for this, by the way, is column generation. It's the same thing. And again, this is mainly the work of Thorsten Joachims and colleagues. As input, we need a training set T with pairs of structured input and structured output. We need sets of feasible configurations, so ones that are not forbidden. We need some tolerated error delta, a non-negative number which the user has to set, and a regularization trade-off parameter C. And the output will be our best set of parameters W. Now we proceed as follows. We define a constraint set which I will define here to be the requirement that the slack variables be non-negative. However, this is a constraint that is sometimes omitted. So in a different formulation, people allow negative slack also. So K is the constraint set. Then we have our parameters W, which are initialized as 0. So this is a vector. And we have a vector of slack variables also set to 0. I'm not sure I mentioned slack variables before. No, I did not. So this would be the place. This is the learning problem, which has a solution only if these inequalities can be fulfilled. However, if I cannot fulfill them, I can introduce some slack here. And this, to prevent these slack variables from becoming arbitrarily large here, I should add another term to the objective function, penalizing these slack variables. And to prevent making the objective ever smaller by just letting these slack variables become more and more negative, it makes sense to put a constraint in here which requires these to be non-negative. So using these slack variables gives me the soft margin formulation of support vector machines. Soft margin because I do not insist that the margin have a specific width, but I allow for a little bit of slack. So in German, man lässt ein bisschen Spiel. However, you don't want too much slack, and this is why you penalize it. This is why it's added to the objective function. Okay, and these are the slack variables that I'm talking about here when I'm writing this variable psi. And we now have a repeat loop in which we first remember what the set of constraints, I should write script letters because it's a set, previously looked like. And then I loop over all examples in my training set. Oh, my handwriting. Okay, for I equals 1 to n. And now, rather than considering all wrong solutions, we only consider the wrongest solution in the following sense. We maximize over the set of feasible outputs that are associated with structured input xi, with the exception of the true output. So y is any legal output except the true one. And I'm now looking for that solution which comes as far as possible to the true one in terms of score, or maybe even exceeds it. So I can look at the difference between the score of the true solution and the score of a wrong solution. Score of the true solution is this one here. It's the score of the true output. And here I have the score of some output y. And the difference between these two I now call the margin. And normally we want this margin to be as large as possible. So we want the true solution to get a much higher score than any wrong solution. But now that we are looking for the wrongest solution, I'm looking for the y that minimizes the margin, or if I want to use a maximization operation here, and I've written the arg max and not the arg min, then I should use a minus here in front of these parentheses. Okay, so we've now found the most wrong solution, and now we can ask ourselves, this most wrong solution, or this currently highest scoring solution other than the true one, is its score so high that we need to worry about it or not? So if the margin that we have just computed, or let me write out the full formula. So so that I can use the y hat, the maximizer from the previous line. So if this thing, so this is the negative margin of y hat. Now let me use the positive margin. So then I should have a minus here and a plus there. If the margin of y hat, remember that we wanted this, if I scroll back up, we wanted this margin here to be no less than 1. And now I'm asking if this condition is violated. So if this margin is less than 1, and if I want to allow for some slack, I can also say if it's less than 1 minus psi I. And if I further want to allow for some tolerance, then I can use this tolerated error delta in addition. Then, so what does it mean? We're looking at the score of the best solution, of the true solution, this is here in green, and we're looking at the score of the best solution. And we ideally want a safety margin of 1. I'm now assuming here that my that this is normalized, the width of the margin by the length of W. And I'm now asking if the best solution other than the true solution, y hat, if it's outside the margin or if it's inside the margin, or if it perhaps even gets a larger score than the true solution. If that is the case, then we need to do something about it. We need to worry. Yeah? And in the then line, we're going to do something about this violation. Then we will update the constraint set. So we say my constraint set K is the old constraint set with the new addition. Namely, I require that this difference here, that the margin be larger than 1 minus psi I minus delta for the specific y. So this should be a y hat. So this is now a literal. This is some output, whereas w in this expression here is a variable. And well, xi is fixed, right? We're in this loop over I. So I or xi is also a literal. In other words, this whole phi is literal. So what we get is a new constraint where w times, and this is also literal here. What we get overall is a new constraint that w transpose times some vector should be greater than 1 minus psi I minus delta. This is a variable, and this is a constant. So I'm trying to make this distinction between literal and variable. So literal means a variable that has been fixed to some value. Okay, we've updated the set of constraints, and now we resolve for the new optimum set of parameters and for the new vector of slack variables. We take these to be the minimizers of a regularization term plus a penalty on the slack variables, one for each input in the training set, subject to the set of constraints in K. And this is now still a quadratic program with, however, a much smaller set of constraints. And so we do this looping over all examples in the training set. And we keep doing this until the constraint set no longer changes. And it turns out that by this procedure, we typically need a much, much smaller set of constraints than the exponentially many ones in the naive formulation. So we can stare at this for a while. And that would also be a good point for you to ask any questions that you have. Yeah. So the expensive step in the procedure is this one here, because we need to run inference. So this is in this case here the parameters have been fixed, and we're looking for the lowest energy solution using the kind of methods that we talked about when we were discussing Markov random fields. And ideally, you should solve this exactly if you can. And if the computational cost of getting an exact solution is forbidding, then you can use over-generating or under-generating approximations. And there is a, I think, 2008 paper by Finley and Joachims that look at the merits of these over and under generating approximations. And in general, the folklore is that this whole learning procedure can suffer or can go wrong if one does not do the inference exactly. But often enough, you cannot do the inference exactly. However, so if you do it exactly, there are some convergence guarantees which you lose if you just go for approximate inference here. And one possible approximation is, instead of the highest scoring solution, to just look for a high scoring one, or as has been suggested in a paper by Luki at CVPR just 2 weeks ago, they even only use a Markov-chain Monte Carlo sampler around the true solution to generate wrong solutions, which are then, however, not used in a cutting planes approach, but in a stochastic gradient descent. So what people do is they use the best maximizer they can afford, and if it's not exact, there are no guarantees regarding convergence rate or even quality of the result. Now, are there more questions or comments? Yeah. So why is the constraint set K much larger than the set of all constraints? Because you can construct artificial mean cases, but leaving these aside, many constraints are loose. So let's say in this feature space phi. So again, phi is a space of fixed dimensionality. And in this space, we have combinations of points. Let's say this was input 1 and output 1, and input 2 and output 2, and input 3 and output 3. We have points that we know from the training set are the true solutions. And then we have many, many wrong solutions. So let's say these are 3 pairs of frames, and these are the true assignments. And then we have solutions that will differ just a little. So for example, this would be x2, but some input, and I don't have a letter for this now, some input which is close to the true solution but not identical, or I could have another point which is very different from the closed solution and far away. And I now have this exponential number here of red points, and that for each of my inputs. So we could say that this is, or rather, I could say that this is the group of wrong solutions associated with my input x1. And then I could have another set of points that are associated with the wrong solutions for, excuse me, that was for x2. And this is the solutions, wrong solutions associated with input x1. And similarly, I have another set associated with the wrong solutions for input x3. And these sets could be totally overlapping. Yeah, there's no reason why they should be separate. And the constraints, the complete set of constraints now say that each of these points should be further than the true one by some margin along our decision boundary. So we create some decision boundary here, which, thanks to the regularization term, has some finite width. So let's say this is the decision boundary, which I parameterize by its normal vector w. And it now has this margin of width 1. Again, rescaled by the length of w. And all of these points which lie on the correct side of the decision boundary, but further away than the margin, all of these constraints are not active. They are not needed to define the boundary. And hence, if I solve this argmin problem, make no difference to the solution. So this is why all of them can be omitted. And what we do here is that we start with, in this cutting planes approach, we start with some solution w, which could be initially randomly initialized, or more typically one sets all the entries to 0. But let's say we have some initial solution w, and first we find the wrongest points according to this initial solution. And for the set number 2, it would be this one here. For the input number 1, it would be that one. And for the input number 3, it would be, let me construct an for the input 3, for the input 3, it would be this example here. And now, using these examples, I learned some new parameter w, which lies, this is not exact now, which lies somewhere along here. And using this new procedure, I now update my estimate for which are the most wrong points. And actually for set 1 and 2, these remain the same. But for set number 3, the now newly wrongest point is actually this one here and no longer that one there. Okay, so if I now resolve my system of equations, I will get a different solution for w, and I thus converge, at least if I've solved my problem exactly. And this minimization is a relatively cheap operation, because our feature map typically has dozens of entries. So we work in a space here with dozens of dimensions, and we have usually not more than of the order of hundreds of training examples. So we have a few hundred green points in this space, and then we generate the red points on demand by this expensive equation here, and this is the hard part. So always to find the new bad points which are used in refining my estimate for the best parameter vector. Do you have more questions? No. Does the process require linear separability? Not in this feature space here, thanks to our use of slack variables. So because we allow for these slack variables xi, we do allow points to be on the wrong side. And this is where much of the robustness of support vector machines comes from. Because if you use a sufficiently high-dimensional feature map, you're practically guaranteed to have separability. Because in such a high-dimensional space, you always find some way to overfit the data and match it perfectly. However, we don't want to overfit, and this is why we allow some slack, which in turn allows the margin to become wide and allows our parameter vector, our W vector, to become short, which means that we have a bias towards making the parameters close to zero, or not using features that are not truly discriminative for making our predictions. However, for this whole thing to work, we do have to be linear in the parameters. So our score needs to be linear in the parameters W. More comments? Then I would like to introduce one more modification. Let's say that I'm trying to see how to modify my picture here. Okay, let's say that if I follow this procedure, we get some vector, some decision boundary W in this space. But let me now modify the set of wrong solutions that are associated with the input number 2 to look like this. And let's say that there is some solution here. It's not very far from the decision boundary, but it lies in a totally different part of feature space. So let me pretend that this solution, this wrong solution, which I'm circling here, corresponds to a very, very wrong tracking. And if I want such a wrong tracking to have a stronger influence on my parameter vector, so having a stronger influence means I would rather like a parameter vector that is biased in the other direction, like this. I want my parameter vector to be shifted such that this very, very wrong solution gets a low score. I think I should revert the signs here of my normal vectors, like this. Then I can modify these equations so as to take into account the different size of the loss. So, for example, I could say in this line here, I could say that I'm not just happy with the margin being larger than 1, but rather I would like the margin to be larger than the loss of yi and y hat. So this is called margin rescaling. We demand that we want to achieve, we want to find a parameter vector W which will give low score to all the wrong solutions, but I want to give an especially low score to the very wrong solutions. And then to be consistent, I should also ask about the loss here in this line, delta I comma y. And when looking for the wrongest solution, I no longer care only about the difference in scores. I also care about how wrong any one solution is. So I'm adding plus this loss to my objective function. And this is the margin rescaled support vector machine. Okay. Any further questions on this?